This example will show how to evaluate a definite integral requiring U-substitution. Analyzing the form of the integrand function, notice how we have an exponent of 3x squared, and we also have a factor of x. Because the derivative of a degree 2 monomial is going to be degree 1, we will let u equal the degree 2 monomial of 3x squared. So if we let u equal 3x squared, notice differential u is equal to the derivative of 3x squared times dx, which is 6x dx. Looking back at the integral, if u is equal to 3x squared, we have e to the power of u, and we're left with x dx, and we have du equals 6x dx, and therefore we'll solve for x dx by dividing both sides by 6. Dividing both sides by 6 and simplifying, we have 1/6 du equals x dx. And now we can substitute 1/6 du for x dx. Before we write the integral with respect to u, we need to be careful here. The limits of integration from 0 to 1 divided by square root of 3 are x values, not u values. We will temporarily leave the limits of integration off when writing with respect to u. Again, x dx is equal to 1/6 du. We will factor out the 1/6, and then we have du. And notice now the integrand function is just e to the power of u, because u is equal to 3x squared. And now here we have a choice. We can find the antiderivative with respect to x and use the limits of integration from 0 to 1 divided by the square root of 3, or we can leave everything in terms of u and find new limits of integration for u. In this video, I will show both methods. Notice the antiderivative with respect to u is going to be 1/6 times e to the u plus c, and we leave the plus c off when evaluating definite integrals, which means with respect to x, the antiderivative is 1/6 times e to the power of u, where u is 3x squared. So if we find the antiderivative here with respect to x, we would use the limits of integration from 0 to 1 divided by square root of 3. We'll come back to this, and now let's find the new limits of integration for u. Notice when x is equal to 0, we have u equals 3 times the square of 0, which is 0. The lower limit of integration for u is 0. And then when x is equal to 1 divided by square root of 3, u is equal to 3 times the square of 1 divided by square root of 3, which is equal to 3 times the square of 1 divided by square root of 3 is 1/3. 3 times 1/3 is 1. 1 is the upper limit of integration for u. And now let's evaluate the definite integral with respect to u. The antiderivative is 1/6 e to the u. Let's factor out the 1/6. And now we need to determine 1/6 times the difference of big F of 1 and big F of 0, where big F of 1 is just e to the first minus big F of 0 is e to the 0. E to the first is e to the 0 is 1. The exact value is 1/6 times the quantity e minus 1. And let's just verify we get the same result if we use the antiderivative with respect to x and the original limits of integration from 0 to 1 divided by square root of 3. Again, let's factor out the 1/6. And now we need to determine 1/6 times the difference of big F of 1 divided by square root of 3 and big F of 0, where big F of 1 divided by square root of 3 is e raised to the power of 3 times the square of 1 divided by square root of 3 minus big F of 0 is e to the power of 3 times the square of 0. And we know from before, the square of 1 divided by square root of 3 is 1/3. 3 times 1/3 is 1, giving us e to the first, or e, minus e to the power of 3 times the square of 0 is e to the 0, which is 1. And of course, we get the same result either way. So I do like showing both techniques because you will see both techniques in practice. And as you move along in calculus, the textbooks show less and less work, and it'll be more common to see a def integral like this evaluated using just the antiderivative in terms of x. And before we go, let's look at the graph of the integrand function over the closed interval from 0 to 1 divided by square root of 3. The function is graphed in blue, And I've already shaded the region bounded by the function and the x-axis over the interval of integration, which gives us this orange area here. Because this area is above the x-axis, the value of the def integral is equal to this area. Remember, this is only true when the area is above the x-axis. I hope you found this helpful.